Good morning, everyone. Today we're going to look at a few exceptions and additions to what we've done yesterday with stoichiometry. Now, the first exception here is when you get to volumes of gases, right? Equal volume of all gases at the same temperature and pressure have the same number of molecules. Since you are grade 11, you've done PV equals nRT. Now, we already know R is a constant over there, but if you've got things that are in the same container, they will now have the same pressure and the same temperature. And that immediately tells you that V is now directly proportional to N. More moles will take up more volume. And if it's double the moles, then you've got double the volume. So what Avogadro actually tells you is if you are looking at gas, and you've got your reagents in the same container, and I don't know how else it's going to react, the volume ratio is the same as the mole ratio. Now, how are we going to use this? If we look at the next example, they tell us to calculate the volume of ammonia gas. So we've got a gas, right? And will be produced when 2,4 cube decimeters. So there, once again, we've got a gas. So they ask us for a gas volume and they give us a gas volume. So when I look at this one, what I would have done before, I would have converted the one they gave us to moles, then work with the ratio, and then convert to volume again. So you would have divided by 22.4 to get moles, and over there you have multiplied by 22.4 to get the volume once again. So since it's the same number, they will cancel out. But we are going to do that by saying when we go from N2 to NH3, now let me just correct that one. Right, so when I go from N2 to H2, I would have used the mole ratio, 1 mole to 2 moles, right? 1 to 2 over there. But what we now have is what Avogadro gave us. If the mole ratio is 1 mole is going to make 2 moles, and these are gases and they're in the same container, then the volume ratio is also going to be the same. 1 cube decimeters of N2 will also prepare 2 cube decimeters of NH3. So the mole ratio is the same as the volume ratio, but remember that is only true when we're working gas volume to gas volume. So this is the exception. If you're going gas volume to gas volume, you don't need to convert to moles first because the mole ratio and the volume ratio are exactly the same. So you don't need to convert. You can go straight from mole ratio to volume ratio. And then if I've got 22.4 of this, I'm looking for that one. Cross multiplications actually just times 2. And I end up with 4,48 cube decimeters of ammonia that is produced. Now, to see if you understand this, pause the video and do the 2 questions that follow, and then just come back to see if you've got it right. In question 4, they tell us that the following reaction takes place in a container where conditions are not standard temperature and pressure. If conditions are not standard temperature and pressure, then that 22.4 is not true and you are not allowed to use that. But here it's no problem. They're asking us to calculate the volume of nitrogen dioxide. So we've got a volume there of a gas. And what they give us is, once again, the volume of a gas. So they ask us to calculate the volume of the nitrogen dioxide that will be produced when 4,86 cube decimeters of N2O5 decompose. So they're giving us N2O5, they're asking us NO2. This time I'm not going to convert to moles. I'm going to say 2 moles are going to produce 4 moles according to the equation. But what do I know? The mole ratio is exactly the volume ratio. So 2 cube decimeters will produce 4 cube decimeters. And then I can just work out how many is then produced by 4,86. So here we can do cross multiplication and you end up with 9,72. So if the mole ratio is 1 to 2, 2 to 4 is the same as 1 to 2. If the mole ratio is 1 to 2, then the volume ratio is also going to be 1 to 2. Now in number 5, They tell us that the following reaction occurs under non-standard conditions. So once again, we're not allowed to use 22.4. And they ask you what volume of ammonia gas. So I'm looking for the ammonia gas. It is a gas and they're looking for volume. So it's volume gas is produced when 4,48 cube decimeters of hydrogen gas. So we're going from a volume gas to a volume gas. So this is one of our exceptions. And here I will immediately say that mole ratio is going to be my volume ratio as well. And then it's easy to see that if you've got 4,48, that is going to give you 2,99 cube decimeters of ammonia. Right, guys, then one more exception. Sometimes there's not an equation, but the thing that they give you, the substance that they give you, is not the same as they ask. So let's see examples of that. How many moles of hydrogen atoms are there in 448 cube centimeters of ammonia gas at standard temperature and pressure? Now, what they ask us here is hydrogen atoms, but what they give us is ammonia gas. And immediately there will be a ratio somewhere to show how we go from one to the other. Now, let's start with what they give us. They give us the volume of ammonia gas. So I'm going to start with that volume and I'm going to divide by 22.4 because now we are at standard temperature and pressure and get the number of moles of the ammonia. But that's not what they ask. They ask hydrogen. So somewhere I will have to go from ammonia to hydrogen atoms. Now there's no equation involved. It's just one substance and I'm looking at the hydrogens in that. So see yourself taking one ammonia molecule and taking all the atoms apart, and then how many atoms will you have? You will have 3 atoms. There's 3 hydrogen atoms in every single ammonia molecule. So here the ratio is something that you have to see from the compound formula. And I don't have 1, I have 0,02 times 3, you end up with 0,06 moles hydrogen atoms in 448 cube centimeters of ammonia gas. So guys, there's 2 more for you to do. Do them first and then come back to see if you've got it correct. Now here they ask you to calculate the number of moles of hydrogen atoms, but what they give us is water. So somewhere along the line, I will have to convert from the one to the other. But first, I'm starting with what they give us. They gave us a mass of water. So let's convert that to moles first. And now that I've got the moles of water, I need to go from water to hydrogen atoms. And for that, I need the ratio. And if you take one water molecule and you take it apart, how many atoms will you, hydrogen atoms will you have? And that's going to be 2. So then it's easy to say, but I've got 0,2 over there, and I will end up with 0,4. And just remember that extra place after the comma. Right, what did you do with number 2? In number 2, they ask us to calculate the number of moles of ions in 200 cube centimeters of a 0,25 moles per cube decimeter, and then they give us zinc nitrate solution. So they're asking us for ions, but they're giving us zinc nitrate. Now let's start with what they give. They give you a volume and they give you a concentration, and this is a solution. So I'm definitely going to work with that solution equation and just substitute to get the number of moles of zinc nitrate. Now guys, you need to know your table of ions so that you are able to write zinc nitrate. Remember, zinc is one of those that's always 2+, and that's why it will bond to 2 nitrate ions. And now we need to go from that zinc nitrate that they gave us to ions. So here we need a conversion factor. If I've got one of those and I take it apart, how many ions? Now remember, don't take the atoms apart. You need ions. And then you will see it's 1 to 3. Because you've got there 1 zinc in there and you've got 2 nitrate ions. So altogether you've got 3 ions. So for every zinc nitrate that you break into smaller pieces, you're going to end up with 3 ions. And then it's easy just to take your 0,05 that you worked out here and times 3 is going to give you 0,15 mole of ions. So that is when you go from one substance to another, but there's no equation. You have to find the ratio yourself.